In this lesson, we're going to be looking at symmetries and conserved quantities, and how they are related by something called Noether's theorem. And it's this theorem and this relationship between symmetries and conserved quantities that really makes Lagrangian mechanics so powerful. So what is a conserved quantity? Well, it's just any quantity that has the same value as the particle moves along its trajectory. That is, any value that doesn't change as the particle moves around. And some examples are energy, momentum, charge, things like that. Mathematically, a conserved quantity is a function of the position, the velocity, and potentially a function of time as well. But I don't think any of the examples we see in this video are explicitly functions of time. And the total derivative of this quantity is zero. And note that this is the total derivative. So it not only takes into account the functional dependence on time. One of the most important conserved quantities is obviously energy. And it also illustrates quite nicely the relationship between symmetries and conserved quantities. So the result is that if the Lagrangian does not explicitly depend on time, then the following quantity is conserved. And this quantity, you may have heard of it, it's called the Hamiltonian. Now this quantity here is maybe a bit complicated looking, but once we actually have a Lagrangian, we do the derivatives and we sub everything in, it will simplify quite nicely and will almost always, although not quite always, be the energy you expected from Newtonian mechanics. And this is a symmetry because we can take the Lagrangian and we can take time and just shift it by a fixed amount. So this is sometimes summarized as time translation symmetry because there's energy conservation. But we'll see how this is explicitly a symmetry later when we discuss symmetries more generally. For now, if the Lagrangian doesn't have a t written anywhere in it, then the Hamiltonian is conserved, or almost always it's energy that is conserved. Mathematically, we can write this as saying if the partial derivative of the Lagrangian with respect to time is zero, which happens if there's no t in the Lagrangian, then this gives us the total derivative of the Hamiltonian with respect to time is zero. That is, the Hamiltonian or the energy doesn't change as the particle follows its trajectory. The proof of this is really just a lot of algebra. We take the total derivative of the Hamiltonian, as given there. We use the Euler-Lagrange equation. So let's look at our first example. This example comes from the pendulum we saw in the last lesson, although we don't really need to care about where it came from for the moment. Although if you do want to look at how the Lagrangian was constructed, it should be in your last booklet. And note that time translation symmetry is a symmetry of this Lagrangian, and we can see that by the fact that there's no time dependence anywhere. There's no t in that expression. And so therefore the Hamiltonian is a conserved quantity. So here I've just got the definition of the Hamiltonian, except I've replaced q with theta. So I've replaced the generalized coordinate with the specific coordinate for this Lagrangian. And then I substitute in for the Lagrangian and do the partial derivatives, and then substitute in for L and simplify everything, and we get our expression for the Hamiltonian. And you see the first term here is kinetic energy, and the second term here is the gravitational potential energy. So if you look, the Lagrangian was kinetic minus potential, and so as you might expect, if we're looking at the total energy, we have kinetic plus potential. This example is for a planet orbiting a star or something like that. I would recommend having a go on your own in your booklet, and then I'll put the answers up quickly. And just as a hint, here's the expression for the Hamiltonian. So pause the video and have a go on your own. Okay, so hopefully you've had a go on your own. So the first step would be to rewrite this expression in terms of all the generalized coordinates and velocities, and then you substitute things in, and this should be your conserved quantity. And notice this is just the kinetic energy in 3D polar coordinates, and then add the potential energy in a gravitational field. This example is mathematically quite easy to work out, but then conceptually interpreting it, it's a bit more confusing. So pause the video and calculate the Hamiltonian on your own, and then we'll come back, I'll show the solutions, and I'll discuss the conceptual oddities with this. Okay, so now you've calculated the Hamiltonian, here are the solutions. Now what's odd about this is that the Lagrangian is just the kinetic energy. It's just the tangential kinetic energy plus the radial kinetic energy. However, the Hamiltonian is the radial kinetic energy take away the tangential kinetic energy. It's not the total energy as we've seen in all the previous examples. And now this often happens whenever a coordinate is fixed externally. So if we were to imagine this, we'd have an angular coordinate and its angular velocity would be fixed. And because it's fixed, it's no longer a generalized coordinate that we can differentiate with respect to. It's just a constant. And so because of that, according to these equations, it just looks a little bit like a potential energy or some effective potential. And in fact, you often get these difficulties whenever something is fixed externally or whenever you are looking at effective potentials. You sometimes get signs which are maybe not what you'd expect. But in this case, we can interpret this or understand this because this is driven externally, because there's energy being put into the system to keep the angular speed constant. We actually don't expect the energy to be conserved. But the Hamiltonian is still conserved. It's just not a quantity we might expect. In fact, what I'll do is I'll link a couple of Stack Exchange posts that look at effective potentials in Lagrangians. It's not necessarily directly relevant to anything we're going to see in the video. They're more just oddities where you get signs maybe not what you'd expect if you don't follow the procedures carefully, but they're still quite interesting to see. The following conserved quantity comes from what are called ignorable or cyclic coordinates. So if the Lagrangian does not explicitly depend on a given coordinate, so in this case qk, then the following quantity is conserved. And the conserved quantity is dl by dqk dot. And this is called the conjugate momentum. Now the proof of this is quite simple. We take the Euler-Lagrange equations. If the Lagrangian doesn't depend on qk, then that term goes to 0. So this means that whatever is in the brackets there, the time derivative must be 0. And so the quantity in brackets is the conserved quantity. We're going back to our example of a planet orbiting a star. What are the cyclic coordinates here? So the possibilities would be r, theta, and phi. But both kinetic energy terms and the potential energy term have r dependence. There is also theta dependence through that sine squared theta. However, there is no phi dependence. There is phi dot dependence, but there's no phi dependence. We treat them as separate coordinates. And so the conjugate momentum is given by dl by d phi dot. And if we calculate this, we get m r squared sine squared theta phi dot. And now this is what you would expect from the azimuthal angular momentum. So in other words, this is called the conjugate momentum because it looks like momentum, or in this case, angular momentum. So as you might expect, the conjugate momentum to something, to the angular dependence, is angular momentum, and it's conserved. We are now going to look at Noether's theorem, and this is probably one of the most important results to come out of Lagrangian mechanics, and it underpins many different areas of theoretical physics. And all the conserved quantities we've seen so far are just special cases of Noether's theorem. So what does Noether's theorem say? It says that for every continuous symmetry of the Lagrangian, there is a corresponding conserved quantity. Now, what does this mean? There's a lot of words in here, so let's go through and break down what they mean. So what we're going to be looking at is essentially coordinate transformations. So we replace the coordinates with new coordinates. So we have our old coordinates, which are given by the little q's, and our new coordinates, which are given by the big q's. And these coordinate transformations are parameterized by some parameter, which we're going to call s. And note that these new coordinates are functions of all of the old coordinates, or many of the old coordinates. So what we do is we take all of the old coordinates qi and replace them with these new coordinates, big Q. But these new coordinates are functions of the old coordinates and some parameter s. Now, what does it mean for this to be a continuous symmetry? So the continuity means that Q, or this big Q, is a continuous function of the parameter s, such that when s equals 0, we just recover our old coordinate system, our old generalized coordinates. And now what does it mean for it to be a symmetry of the Lagrangian? So far we've replaced the coordinates, we've seen what it means for this replacement to be continuous. What does it mean for it to be a symmetry? Well, what it means is the Lagrangian doesn't depend on this parameter s. So the Lagrangian is unchanged by this coordinate transformation, or at least unchanged to first order in s. So some books and some notes make these infinitesimal and you would kind of Taylor expand big Q in terms of s. We're not going to do that. We're going to say that it's a symmetry if the derivative of the Lagrangian with respect to this parameter is a 0. This is exactly the same as saying the coordinate transformation gives no first order change, or if you make infinitesimal transformations, then there's no change. But people might not be comfortable with dealing with infinitesimals or things, but we make the coordinate transformation and the derivative must be 0. That's an alternative way of saying it. It's the way we'll state it here. I'm just saying some notes will say it differently. And now, if these conditions are met, so if you replace the coordinates with new coordinates in a continuous way, and the derivative of the Lagrangian with respect to this parameter s is 0, then there is a conserved quantity. And the conserved quantity is given by this rather complicated expression here. I mean, it looks fairly similar to some of the expressions we've seen before, but it's a bit more general. And this is, well, we could just call it the conserved quantity, but some people call it the Noether charge. And the proof for this is in your booklet. So I would pause the video and go through that proof. It just involves taking the derivative of this expression, but there's quite a lot of algebra. So I would pause the video and work through that proof. And it should also be enlightening about what some of these definitions mean. It would be a bit more concrete than just the definitions on the screen. This example is potentially going to be quite confusing, so I'll go through it slowly. And it may appear that the symmetries I just had to tell you, and unfortunately in general, you do just have to spot the symmetries. Sometimes you might expect them if you kind of know what if you've seen similar Lagrangians before, but in general, you do just have to spot them or know what they are. So the first symmetry of this Lagrangian is just to replace little x with big X, where big X is little x plus s. So we've just done a constant shift. So the coordinate transform is just a constant shift of our x coordinate. And then the corresponding velocity, big X dot, is just equal to little x dot. This s parameter doesn't depend on time, so when we do the time derivative, it vanishes. And if we were to substitute this into the Lagrangian, then nothing would change. We'd just be replacing x dot with x dot. So nothing has changed. The Lagrangian is unchanged. Therefore, the derivative with respect to s must be 0, because there's no s in it at all, and therefore this is a symmetry. and therefore we can calculate our conserved quantity. The expression is given here. We substitute our expression for big X in, and we end up with just mx dot, which is exactly what we saw in this example before for a cyclic coordinate. So we can see that cyclic coordinates are just a special case of Noether's theorem. So we saw that the Lagrangian doesn't depend on x, so we can shift x by any amount s, nothing changes, and we get a conserved quantity. And that's just because the Lagrangian doesn't depend on x. The second symmetry is a bit harder, and it's going to involve both z and y. So we shift z by an amount epsilon, where epsilon is the parameter this time instead of s. We could have given it any letter really, but why not epsilon? And then we also, at the same time, shift y by an amount g over 4 epsilon. Now this is one symmetry, so they have to have the same parameter. We're changing both z and y simultaneously. So they've got the same parameter, but notice they have different coefficients in front of the parameter. And we'll see why that's necessary in a second. And then similarly, the generalized velocities related to big Z and big Y, just little z and little y dot. So now let's make these replacements. We take our Lagrangian, and I've replaced y dot and z dot with big Y dot and big Z dot, and I've replaced z and y with big Z and big Y. Now let's replace big Z dot, big Y dot, big Z, big Y with the coordinate transforms there in terms of little z, little y, and epsilon. So the kinetic energy just goes back to y dot and z dot, but the potential energy has a slightly more complicated expression. But I have just substituted in from above. But if we were to expand those brackets, the two terms with epsilon in would cancel, and so the Lagrangian would end up exactly the same as it is above. So once again, the Lagrangian is unchanged. And therefore we can calculate our conserved quantity. Here we have two terms to include. We substitute everything in, we do the derivatives, we add the two terms, and we get our conserved quantity. And in this case, our conserved quantity, we see it's a combination of the z and y momentum, but a special combination of the z and y momentum. Neither of them are conserved individually, but this combination is conserved. How did I spot those symmetries? Even though in general you may just have to spot them and maybe get lucky, because that Lagrangian was linear, I maybe expected the form of the transformations to be the coordinates plus a constant. That is, I expected linear transformations or linear symmetries where I take the coordinates and just add a constant times the parameter. But there's still the question of how do I work out what the constant is without just trying and guessing. We'll see that there is a systematic way to do it. So let's substitute these new coordinates into the Lagrangian we had. We do that. In all the cases, the kinetic energy is unchanged, and then I've replaced z and y with the new values, or the new coordinates. And then I require that the derivative of the Lagrangian with respect to s equals 0. And if I differentiate this with respect to s, I get this expression here. I'm going to need this to be 0. And there are two linearly independent solutions to this. Firstly, is I can set kz and ky to 0, and then kx can be whatever it wants. And I'll just set it to 1, because an overall scaling won't affect anything. I can just set kx to 1. The other solution is kx equals 0, and kz and ky have the combination we saw before. This example is quite complicated, so I'll tell you what the symmetry is, and then it will be your job in your booklet to prove that this is a symmetry, and then calculate the conserved quantity. So the symmetry is this combination here. And for those of you who like to visualize things, this is a rotation in the x1, x2 plane. If you don't like to visualize things, well, it's just a function. So now, on your own, from these, calculate the generalized velocities. So big x1 dot and big x2 dot. Substitute everything into the Lagrangian. Show that this is a symmetry. In other words, show that the Lagrangian, or the derivative of the Lagrangian with respect to s, is 0 after you've substituted everything in, and then find the conserved quantity. Now you've had a go on your own. I'll put up the solutions, and you can check. So the general form of the conserved quantity is given here, and note we have to set s to 0. And I'll do each partial derivative individually. The first partial derivatives given by this, with the factor in front of the brackets, comes from the derivative of the Lagrangian, and the factor inside the brackets comes from the derivative of the coordinate. And then we set s to 0, and we get this. Similarly, for the second set of partial derivatives, the factor outside the bracket comes from the derivative of the Lagrangian. The factor inside the bracket comes from the derivative of the coordinates. And then we set s to 0, we get this. And then the conserved quantity, we add both of these together. So a conserved quantity is this combination here. We're now going to look at a very important symmetry that comes up a lot. That's translation invariance, or translation symmetry. And in this case, the conserved quantity is the total momentum. So let's look at an example, and I'll just show you one because all examples are basically the same. Okay, so this is our Lagrangian, and this is the Lagrangian for two particles connected by a spring with constant k, or it could be the Lagrangian for something like a diatomic molecule where k represents the force between the two atoms. And the symmetry in this case is if we take both x1 and x2 and we shift them by an amount s. So that is, we take both coordinates and we shift them by the same amount. Or we take our diatomic molecule and we just move it s meters to the right. In this case, we calculate our conserved quantity and we just get the total momentum. Note that each momentum individually wouldn't be conserved, but it's the total momentum that is. So we couldn't shift x1 by s and leave x2 alone. We couldn't do that. That wouldn't be a symmetry. We have to shift everything together. And then the conserved quantity is the total momentum. If this were a 3D system, we could shift all of the x coordinates by an amount s and we'd get x momentum as our conserved quantity. Similarly, we could shift all the y's by the same amount and we'd get y momentum as our conserved quantity, and so on. But whenever you can shift some of the coordinates, the conserved quantity is momentum. Another really important symmetry is rotation invariance, and this leads to angular momentum conservation. So just as translation invariance led to linear momentum conservation, rotation invariance will lead to angular momentum conservation. So let's look at an example in 2D. So here we've got our Lagrangian, and it's already written in terms of polar coordinates, and we've got any central potential. So the potential is just a function of r. And the symmetry in this case is we take theta, and we can just shift theta by an amount. So we just rotate the entire system. And then if we work out the conserved quantity of this, we get, as we'd expect, angular momentum. That last example was maybe quite obvious because it just was a cyclic coordinate, but not everything with rotation invariance is going to be in polar coordinates. So let's redo the example, but this time in Cartesian coordinates. So here's the same Lagrangian, but in Cartesian coordinates. And you see that the potential is still just a function of r. This is r is now x squared plus y squared. Now the symmetry in this case is a rotation in the xy plane. And this is exactly the same symmetry as we saw for a previous example. The previous example wasn't meant to imitate a particle moving in 2 dimensions, but we saw a symmetry like this where it was a rotation in the x1, x2 plane. And so you've already got the algebra in your booklet, so I'll go through this very quickly. So if here's our symmetry, we've already worked out the conserved quantity, and it's going to be this. Now, on your own, if you make this substitution, then you will get back to exactly the conserved quantity we had on the previous slide. That is, we go back to angular momentum conservation. It's just written in a different coordinate system. And also, in the suggested reading, they go through similar examples, but in 3D. The end result's the same. Rotation invariance leads to angular momentum conservation. But in 3D, you can rotate in 3 different directions, so you have 3 conserved quantities. And you have to do a lot of vector algebra. But that's all in the suggested reading. But in summary, Noether's theorem tells us that symmetries of the Lagrangian give rise to conservation laws. So for every symmetry, there is a conserved quantity. The conserved quantity of energy, or the Hamiltonian, for being precise, comes from time translation symmetry. Momentum comes from spatial translation symmetry, and angular momentum comes from rotational symmetry. And of course, there could be other conserved quantities from other kind of less common symmetries.